morning and thank you for joining us. Today's webinar is on BrewWorks, an in-depth look at hops analysis. We will be taking questions at the end of, we'll be addressing questions at the end of the webinar, so feel free to submit your questions throughout the presentation. Our first speaker is Tom Hartline. He is our SVOC product line manager, and I'm going to turn it over to him.
Thanks, Shelley. Good morning, everyone. As Shelley mentioned, we're going to look at different things or analyses for hops. We'll start with terpenes by Headspace, pesticides using a QuECHERS extraction, and then my colleagues will take over the metals portion for those elements. So we have a lot of material to cover, so we might as well get started. What we looked at is essentially 5 commercially available hops. So we have a Cascade, a Centennial, Nugget, and a Mosaic. And then we have what's called a CTZ, which is a blend of the Columbus, Tomahawk, and Zoops. So primarily what we're looking at here is essentially 6 terpenes of what we were interested in for the Headspace portion of this. So they are associated with the different types of aromas and taste native to that hops plant. So the main ones we'll look at are carpylene, humulene, limonene, linalool, myrcene, and pinene, which are highlighted in red. Our analysis uses a static headspace technique, which is a very common technique for VOCs. It's pretty rugged. Basically, you don't have any problems associated with injection ports or column degradation because everything is done in a gas phase. Here at Teledyne Tekmar, we've been doing VOC concentration for many years. We are probably the market leaders in Purge and trap. And then, of course, we have static headspace, which we'll look at in depth. And we also have a dynamic headspace, which essentially puts a trapping mechanism into lines so that you can concentrate compounds to increase your sensitivity. The 2 models we see here are the HT3, which is our static and dynamic mode, so you can use a trapping technique or a standard static. And then the Versa, which is a lower cost static only model, that's what the fingerprinting was actually done on. Here we see a video of the basic headspace technique, although it looks like this video may not be coming up. So I'm going to apologize for some difficulties. Hopefully that's all corrected. What we see here is pressurization of the sample. So we let the sample come to its temperature equilibration, and then we're going to pressurize that sample so that we can extract that headspace. Also, this flow diagram shows that trap, which is right now behind what you're seeing in the pressurization step. But we can alter our flow path to constantly sweep the headspace to the trap. So once we pressurize, we're now going to go ahead and fill the loop. So you can see the gaseous aliquot is now leaving the headspace vial, and we use a fixed loop there. It's a 1 milliliter loop. As you can see, that just vents to atmosphere. I apologize for being ahead of the video. Then once that's done, we're going to have to introduce it to the GC. So we reroute the GC carrier gas. It's going to go through the loop and take our aliquot over to the GC for separation and detection. So what we used here was a method optimization mode to find the best conditions for this analysis. What the method optimization mode does is it lets you vary any of the variables within the method to get the optimum performance. This screen that you see here is our temperature study. So we started at 40 degrees and then we went up 10 degrees up to a final value of 190 degrees. You can also do those in duplicate or triplicate if you wish, but we used a single stepping for this technique. And what we found is to the left is our temperature study. So you see all the way up to 190. This is a single test hop to get the optimum performance there. And then the same thing was done on the time study. So once we had those dialed in, we went and created our method. So we did what is considered a flash evaporation technique. So we took 10 milligrams of each of the hops. Again, that would be the Cascade, Centennial, Nugget, Mosaic, and the CTZ. Primarily what we focused on, we set a pressurization to 20, and then we did a 10-minute sample equivalent time to let everything get into the headspace. So now that that was finalized, we actually got to look at some of the hops. So this is the Cascade hop, and as expected, the myrcene, carefulline, and humulene are the primary terpenes that we're going to see, and that's pretty common through all of them. But you do see some other compounds rising and going on different hop varieties. So essentially what we wound up doing, I'm going through these rather fast just to give you an idea that they're all quite similar. And ultimately, if we look at an overlay, we can see the 5 of them all looked at the same time. And again, we can see the myrcene, the carefulline, and the humulene are the major components. But we were also interested in the ones that actually add some other citrusy flavors or floral aromas. So we looked at the other 3. So here on the left, we can see pinene, and we see that Centennial has more of it prevalent than the other 4. The myrcene was dominated in the CTZ blend, and limonene, it was more prevalent in CTZ. However, the Nugget had more of the linalool. And then the last 2, pretty much strong in all brands, but the CTZ had the most that we can see there. So essentially, that was our headspace analysis for the FET technique. Again, you can use a dynamic option if you wanted to get more levels of sensitivity. With headspace, we find it's a rugged and easy technique to profile the terpenes. And of course, we can use that method optimization mode to tailor a specific method requirement. Perhaps you're looking for something else that you have to change some of those parameters. With all that being built into the software is a nice feature of both systems that's available on the Versa as well as the HD3. So next we looked at the pesticide analysis. Pictured here is our Automate Q40, which we'll see in a couple more slides. We used a QuECHERS technique. For those of you that are unfamiliar with QuECHERS, it's been around, probably since 2002, but the adoption methods are the AOAC method and the European norm method. Essentially what you do is you homogenize your sample, and you're going to add a solvent, acetonitrile, with internal standard. You can vortex that, then you add a salt, magnesium sulfate with some buffers, and then you shake that, centrifuge it, and then once it's all been spun down, you take that aliquot and clean it up using a dispersive solid phase extractive material, primary, secondary amine, and magnesium sulfate. And again, you shake that and centrifuge that, and from there you take that final extract to either your LC or GC for analysis. The Automate Q40 takes that whole piece from the homogenate to that final extract and automates it. It can do 40 positions, and depending on the method, you can look at run times anywhere from 4 to 8 hours, depending on what type of method you're doing for 40 samples. And it uses standard 50 mil and 15 mil polypropylene centrifuge tubes. So for our method, what we did is it's a modified QuECHERS extraction. So we use the unbuffered salt. So we add 2 grams of our ground hops, and then the system's going to add 10 mils of water, 10 mils of acetonitrile, and add the internal standard, which was TPP or triphenylphosphate. And we added a premix of 5 grams of the extraction salts. Again, that would be the unbuffered salt. That's automatically added by the system. Then we shook the sample for 1 minute, centrifuged it for 5 minutes. Then we took 6 milliliters of that supernatant to a cleanup tube, which had 900 milligrams of magnesium sulfate and 300 milligrams of an aggressive cleanup Z-Sep. Then we shook that for 30 seconds, centrifuged for 5 minutes. From there, we diluted 10x into our mobile phase, and then we took it to our LCMS-MS for analysis. Setup for the LCMS-MS can be seen here. So we used a biphenyl column. You can see the mobile phases are ammonium acetate, water, and methanol. 0.5 mil a minute for the flow rate with the temperature of 35. To the right is our pesticide spike. So you can see the commercially available pesticides we use there. And then for the MS section, here's the transitions and so forth for the compounds that we looked at. As you can see, the spike recoveries were acceptable. We had some suppression at difenoconazole, but other than that, all the recoveries were within their expected ranges. For the actual hops analysis, this is unspiked. We really didn't find anything, which is a good thing. We did find some boscalid in a couple samples, as we can see here, but it had very low concentrations. So the first one we see is a Cascade hop. So we can see the boscalid there, as well as our standard. We also seen a bit of it in the CTZ. Again, not much to report, but still there. And then very low below our detection limit in the Mosaic. So essentially the extractions were done using that automate, and all of our recoveries are what we expected. And again, we didn't find too much of anything there, which is a good thing. What we found is that the automate can be used to run unattended. We used a modified QuECHERS technique. Of course, you can create your own method using the automated platform if you like. And then you can use custom cleanups to remove any of those interfering compounds that are very inherited to the hops matrices. It's a bit of a messy extract. All in all, we thought the testing went well and the results were what we expected. And with that, I believe I'm going to hand it over to Manny, who is going to talk about some metals by ICP.
Okay. Good morning. My name is Manny Almeida. I'm the ICP product manager at Teledyne Leeman Labs, and we did the trace metal analysis portion for this hops work. Okay. We did the trace metal analysis on two versions of the hops. We used the Nugget and the Centennial hops. We did not do some of the other ones. Those are the ones that we were sent. I had no idea there were so many different hop types. That's one thing I've learned through this work. For trace metal analysis, hops is one of the sources of trace metals introduced into the brewing process. Other places where trace metals are in the raw materials, things like barley and malted barley that pick up trace metals from the soil, from the water, from the fertilizers that are used. The different types of flavorings and spices that are used are also sources of trace metals. Process aids, linings of kettles, things like that, filtration aids, diatomaceous earth, all contribute raw trace metals to the brewing process. And also the brewing process itself, the tanks, pipes, copper equipment, all can have an effect of adding certain trace metals to the final products. And depending on the concentration, trace metals can have positive and negative effects. There are some trace metals that you want to be in the process, and there are some that you don't want. And even some that are beneficial can be problematic at higher concentrations. So, for example, elements like zinc have positive effects. They increase fermentation rate. Copper can reduce sulfur flavors by oxidizing sulfides. Manganese can help activate some enzymes. But at high concentrations, zinc can introduce a metallic taste to the product. High concentrations of copper are toxic to yeast and also oxidize the product, causing shortened shelf lives. And manganese also can be toxic to yeast. And each of these metals also has other effects, positive and negatively, just looking at a few. So for the trace metal analysis, we used ICP-OES. That's inductively coupled optical emission spectroscopy. Can provide simultaneous trace metal analysis of up to 70 elements in the periodic chart. And depending on the model or the type of instrument, you can do analysis from the part per billion up to the % concentration range at one sample run, depending on whether it's an axial, radial, or a dual view system. The instrument that we use for the trace metal analysis is our ProdigyPlus. the latest model of ICP. Some of the salient features for this analysis was a demountable low-flow torch. Users are interested in reducing argon consumption. The demountable torch allows you to do that. A new detector type that increases linearity and speed. We'll look at it very briefly. And this instrument also has the ability to analyze or determine halogen concentrations, chlorine and bromine, which we did not do in the for the hops analysis, but it is a feature of the instrument. Okay. The twist lock torch that we have is designed to make the instrument easy to operate, comes apart very easily, can replace just the injector. It is mounted on an alt-tem bayonet that provides also the gas connections and positioning of the torch. This is an example of the sample introduction system, and if you can see off where the torch goes into that plastic, that white plastic block, there's a scale there that allows the positioning of the torch to be repeated from day to day from different operators. When the torch is replaced or removed, it will automatically do all the gas connections, so you don't have to worry about connecting up. There's no torch arms to break, and you cannot connect the gases incorrectly. This was a dual view instrument, so we have the ability to look at both axial and radial views. For this particular analysis for the hops with the trace metals, everything was done in the axial view. Concentrations for the trace metals were somewhat low. If we wanted to do some different elements like calcium, magnesium, which can be present at very high concentrations, we would have done those on the radial view. Okay. And just an example of the scale. So the scale that's shown there will allow people to remove and replace the torch in the exact same location. If you have high dissolved solids or different types of samples, this will help you place the torch in the optimum position for each one of those analysis. And when the torch is removed, you can see in between there these little gas, these are the gas ports. Once the torch is located in the system, the gas connections are made. Those O-rings provide the difference between the auxiliary and coolant flows. So replacing the torch and putting the torch in the system is fairly automated. Okay. The instrument also has a detector, new detector based on CMOS technology. Some of the advantages is this detector has much greater speed than the detectors we've used in the past, so it improves linearity for analysis, but it also decreases analysis times. The readout is quite fast, so this results in a higher sample throughput and a lower analysis cost, because we're not spending much time actually collecting transferring the data down from the system to the PC. So we get to the analysis. Sample preparation, we chose simple hot plate digestion. We could have done this via microwave, but it was actually quite quick. So we took ½ gram of sample, some DI water, some nitric acid, heated it up at 95 degrees for about half hour or so, cooled it, added some peroxide, heated it again for another half an hour, then cooled it, filtered it, and then diluted everything with to 100 mils with deionized water. So we looked at the Centennial hops. We also did a prep where we spiked all the elements of interest at 100 ppb. We looked at the Nugget Hops, and then as sort of a method validation, the closest thing we had was we took some NIST spinach leaves and carried that through the same hot plate digestion. Okay, the elements that we looked at are elements that are somewhat commonly done in some of the brewing process, particularly when people are analyzing wort solutions, and with using basically the primary wavelength. So we're expecting the concentrations of all these to be actually low, so we picked the most sensitive wavelengths for those elements. Typically, we would also do multiple wavelengths of each element as a check on potential interferences. We did that. We didn't see any different results from the different wavelengths, so we're not going to report the data on all the wavelengths just to make the slides a bit easier to read. The parameters for the analysis, whenever you have a method and whatever parameters are set, those will also be recalled. So we chose the power at 1.2 kilowatts. We ran the coolant flow a little higher than usual. we did the analysis was fast because of the detector, so we were able to run at sort of full flow. The torch can run anywhere from about 10 up to 20 liters a minute. A little bit of auxiliary flow, a little bit of dissolved solids. The neb pressure, we used a sea spray neb, which is high solids nebulizer, and a glass cyclonic. And the torch had a 2.5 millimeter bore injector. There are different injectors, bores available depending on the analysis. For example, to run something in an organic sample, you choose a smaller injector bore. And the uptake rate set at about 25 RPM, which translates to approximately about 1 mil a minute or so. Okay, automation. We set the run up on an auto sampler. We used a CTAC ASX 280. You can see on the right-hand side the setup for the run. So initially, we're going to run the calibration for the standards. We'll run a QC, where we ran the 5 or the 4 samples plus a spike in there, and then close the analysis out with the QC. Right. For the automation, we can, after we run the calibration, we run a check standard. That check standard does not pass the criteria. In this case, we set it up at plus or minus 10%. We would recalibrate and rerun, and we also closed it off with another check standard with the same failure action. There's some different failure actions that you can use to go ahead and ensure the analysis integrity over the run. Okay. Calibration, we use standards from 0 to 250 ppb, and overall, so we see a typical calibration curve on the right-hand side. The precision ranged in this particular case from 0.3 to 0.9%. Typically, at this level, most of the RSDs on the standard should be less than 1%. And data was collected in a 5 by 29 pixel subarray. All the wavelengths that are used exist in a subarray of a certain size depending on the wavelength. Could be up to 29 pixels wide or up to 57 pixels wide, and that allows you to do background corrections in more complicated matrices by manipulating the size of the subarray. But all the subarray sizes that we use were all selected by default. Just as an example of the type of what the data looks like, these are wavelength scans of the standards along with the 2 samples, the Nugget and the Centennial, showing an overlay, one for copper on the right and zinc on the left. If you look at the wavelength scans down below, in the middle of the screen, you see a sort of a green rectangle. That's where the actual measurement of the peak is going to be done. The 2 blue squares to the left and right on both of them are where the background correction points are going to be done. The correction points can be anywhere within that window. They can be different widths to get better background correction, particularly at low concentrations. Another thing to point out is all the data here is stored so that a user can come back and make modifications to the data, change background correction points, change the peak location, change the curve fit, concentrations of standards, and go ahead and recalibrate or recalculate data without having to rerun the sample. Okay. So some of the results that we got, so for the NIST, the 1547A spinach leaves, for the elements that were of interest that we ran, you can see on the left-hand side what the certified result and the percent recovery, and percent recoveries are all within expected range. We like the percent recoveries to be within about 85 to 120% or so. We're actually tighter than that. 90 to 110 is what we really like it to be. So we're within the accepted range there, so that's good. We're happy with that result. Then I'm looking at the Centennial hops. Again, you can see the recovery of the 100 ppb spike on the right-hand side. So to point out, the spike for the manganese and the iron were actually higher than the 100 ppb because the concentrations wound up being so much higher than we had expected. We had not run any analysis on hops, so we didn't know what to expect. So the iron and the manganese were a bit higher than everything else. So we modified the spike recovery standard. I think was about a half ppm or so. So this is fairly typical results, we think, with good recovery. We did have higher manganese and iron than we had expected. So these are the results for the Centennial. For the Nugget Hops, we also noticed that the iron and the manganese were elevated too, and they were actually quite close together. We thought that we had perhaps had some contamination in the sample prep or in our water, so we repeated the analysis, and we wound up getting pretty much the same results. So be interesting to see, maybe look at some of those other hops to see if they have high iron and manganese concentrations also. But these are pretty typical results, nothing of really too high concentration in there. And you can see the precision on the right-hand side as the concentration gets lower at about, like for cadmium, at less than a ppm in the solid, as you would expect for that. The cadmium and the lead at the lowest concentrations, the RSDs become progressively poorer as you approach the minimum detectable levels. Okay. So, I mean, in conclusion, ICP, the ProdigyPlus in particular, is an excellent tool for trace metal determinations in brewing materials. The spike recoveries in the reference material indicate the method is suitable for the analysis of hops. The good spike recoveries indicate that we don't have significant matrix interferences, so we didn't need to run the analysis via method of standard additions or to use an internal standard. And finally, the sample preparation simply via hop plate is simple and fast and provides accurate results. And that is the end. And I guess we'll take questions towards the end, but thank you very much for your attention.
Okay, we're turning this over to John McWatters now. Just a second while he brings up his screen.
Good morning, everybody. I'm John. I'm the Mercury product specialist based out of Omaha. I was sent the two samples, the Centennial and the Nugget, for analysis of Mercury. It's kind of interesting in researching this with that they come from the largest portion in the U.S. comes from the Yakima Valley in Washington State, and various areas there specify different types of hops. I ran the system. I could have done a liquid digest with acids and permanganate and the like other plant tissues, but I chose for quick and easy, and I set up the Hydra AA, the 2C, to do it by combustion analysis. A quick overview of the system with combustion. It's very simple to run samples of this nature. Not to belabor the point, but you weigh out a sample into your sample boat. When you're doing samples that are fairly low, like these hops turned out to be, you want to make sure that you pre-clean your boats well so you don't have any background to add some plus and minus. The system injects the sample, or you can run it manually. So you can have the boat go into the system. It heats it up. First it dries it, then it heats it up to combust everything and break the material down and release the mercury. The catalyst tube has several chemicals in there to help further break down the combustion products, and to pass then the gases that are produced from that combustion pass through the Nafion dryer where any moisture is reduced, and that's going to help give us a better signal further on when we go into the flow cell. Everything that's coming off the sample as it's being burnt, the mercury is trapped on the gold. Gold amalgamates the mercury, and when we've concentrate the mercury to get us a strong solid spike. Once that happens, the system goes to the purge mode, and the gold trap turns on the heat from the gold trap heater, kicks the mercury off the gold, and then we go into a system of long and short cells where we can get two different peaks off of the same sample injection. The sample handling was quite easy. I didn't have to do any prep. It came pre-ground and looked pretty uniform and homogeneous. So I simply did a little bit of testing early on to see how homogeneous the samples were. I did 3 or 4 samples, subsamples of each variety, looking for anything that I needed to tweak or change my range. I used a range that was very significantly low, since it turned out these were going to be fairly low. The system can be ran in such a way that you can actually hook up a scale, input the weight via the scale. You can manually do it, as I did in this first initial steps, in the pre-steps here. The graphic where the sample is being ran there is you simply type in the weight, set the boat on the forks right before it goes into the oven for drying and combustion. That's one way that you can do it, or you can also set it up in such a way that you have your boat shuttles and load up everything in a boat and have that on the shuttles to run through the system in an automated fashion once you set up your method parameters. The method parameters that I used for this one are fairly generic. There's several different types of setups in the manual for different types of samples that are a little harder to get the mercury out of the particular matrix. There's several different configurations. I chose something that was fairly similar for really, really low samples like this. The screen on the graphic on the right shows basically the flow through of the sample as it goes through the system. It'll, as I said, goes through a boat, loads up into the system, is heated, dried, combusted, and then the gases flow through the different size cells to give us 2 peaks. In this particular case, since it was so low, I only used the long cell, the most sensitive cell. Standardization is just very simply, I create some liquid standards. You can also use solid reference materials of a specified concentration to set up the system. I went with liquids. I created a concentration in a particular range to range in the final range that I have here on the left side, were my actual standards that I used. Those are injected into the system one by one, automated fashion, and it develops a curve of the mass versus the response, or the microabsorbance in this case. Here's actually the calibration. If you notice, there's on the blue boat shuttle there is a missing space on the first one there. I always like, when I'm starting a calibration, to run a no boat blank, is what I call it, and that cleans out anything that's in the system, because this first one that is actually just starting to go into the oven is my blank for my calibration curve. I had a really nice calibration curve you can see on the right-hand side. I think I got 5 nines, which is sometimes a little bit harder to get. Got to be very careful and very clean with all the boats. I pre-cleaned all my boats before I started any analysis, whether it was the calibration or the actual samples. The first one I did was the Nugget, and when I did the actual testing, you can see that the boats are very full. I filled the boat to capacity since the samples were quite low in mercury, and I tried to get them all cleaned off as well as possible, or make them as uniform as possible. The system will, and you type the weights in as you go along, so the system will account for whatever differences there are in the actual amount of sample that you're adding in there. I did the Nugget first. I did 7 reps to develop some plus and minus references later on. After the Nugget, you can see that I didn't quite get back to the instrument to take a snapshot quick enough, and that the first sample of the Centennial hops had already gone into the oven. As the samples go through the process, when they're loaded up in the boats, as the last boat and, as the last rack finishes, it gets pushed off onto some forks for so that the next set of boats can go into the load up position. Here's the very end. I caught it when it was picking up the last boat after that, and you can see on the right-hand side an example of the actual peak. The green peak that you see on the right-hand side is the longer cell, the one where the most the light goes through the most sample. And then on the right side, when we're getting in higher levels, is where we have a smaller peak. It's a very short cell. It's a 1-inch cell as opposed to the 10-inch cell to give us a greater dynamic range. This was the once the system was done with both sets, in order to create a printout or to send it to a LIMS, you can set up a CSV file or printout. You simply drag which samples or click on which samples you want to do in your report. You grab a report spec, which is basically what I want on the report, and you tell it where I want it to go, either to a CSV file or over to the printer. I created a CSV file just to try to make the numbers look a little bit easier to glance at and see what was going on. And then since there was some moisture associated with these, we want to subtract that out so that we're getting on an as received or a dry weight basis of the final concentration. So I dried the samples tried to shoot for 100 to 110 degrees for 2 hours. I measured at 1 hour and 2 hour and 3 hour until I had a constant temp on a hot plate in a airstream in a clean hood. The the percent moistures are on the right-hand side, and it's interesting that when I was looking up some of the particulars about hops, it says when they're prepared and dried in the kilns, it is normally between 7 and 9% moisture. So I felt like I came out pretty close on that. The results is for dry basis. We can see the repeats here on the Nugget. Everything was going along really nice, and I did have one that you could consider an outlier, was slightly higher. As I said before, the samples were all very well uniform looking and well mixed. There was 1 or 2 small pieces of unground material that I might have gotten a piece encapsulated in my first grab there. So that's probably why number 7 was a little bit off, and it did kind of ruin my my overall RSD there. It was much better on the Centennial hops. Overall, the actual concentration was extremely low for mercury in the hops. And here is just graphically glance at it, much easier to read the concentrations and recoveries. A few quick notes of some of the features I used or didn't use. As I said, you can set up the instrument. You can connect it to a scale, and actually, as you weigh them out, the system will input it into the sequence page for you to make things go a little bit faster. There's a preload technique. If these had been very much lower, I probably would have tried to use the preload technique because you can only squeeze so much sample into the boats. The preload technique is simply taking a boat and then another boat and then another boat until you feel like you're going to get the right concentration where you're in a good detectable range. And then all of those individual boats are burnt onto the gold trap, and at the end it's just an accumulation of that, and then it takes the final analysis for that one. Also, just a quick note, if you are interested in running samples of this nature and you already have an instrument, a Hydra 2 instrument, there is a completion kit, or excuse me, a transfer kit where you can simply just change out the bottom of the analysis. The actual detector head above is where the cells actually live, and you can actually just change how you introduce the sample, liquid or solids. We chose this one because of it's so much quicker and easier just to throw the samples on, check for complete combustion. We had good ability to see the relatively low concentrations without using the preload to save a little bit of time. If we use a combustion technique, you don't have as many steps preparation-wise, and you create a lot less acid and waste products that can cost extra money to get cleaned up or transferred out of your lab appropriately. You normally have to spend quite a bit to have those hazardous wastes taken away. And I guess now Shelley is going to entertain questions and throw them out to us.